All right, so welcome to the presentation that would seal the deal about as for the topic of radioactivity, entry-level radioactivity, and its interaction with absorbing material from the 10th lecture. This is a good time when we're talking about lecture to credit Professor Verade for creating such an awesome presentation we can use and understand. We're going to discuss the interaction of radiation with absorbing material, what is linear energy transfer, what is penetrability, and the basics of detection of radiation. So let's get started. Let's get this show on the road. And when we're talking about interaction of radiation with absorbing material, really we're talking about how do alpha particles, beta negative particles, and gamma photons, also particles, you can say, interact with absorbing material. And if I'm wondering how the alpha particle interacts, I need to understand that the alpha particle is basically two neutrons and two protons. And I need to understand, I need to compare it really. Let's compare it to a beta negative particle. We're saying beta negative electron is the same thing really. And an electron is about 1 to 2,000th of one atomic mass unit, which means that it's almost 1 to 2,000th the size of these guys here. So if I draw an alpha particle and I compare it to a beta negative particle, maybe the beta negative particle is going to be this little dude down here. So compare this one to this one, and you'll probably understand that this alpha particle, when we're talking about radiation particles, is massive. It is a massive, massive particle. So let's compare, and obviously, when alpha particle is moving through a material, what is it going to do? Well, basically, material is made of atoms that are surrounded by electrons, and here I have a very massively charged particle that is very, very, very big. And again, a double positive charge is a very massive charge when we're talking about charge moving through tissue. So it's going to attract a lot of electrons. Electrons are really going to want to interact with it as it's moving. And obviously, because it was given some sort of kinetic energy, let's just say it had 100% kinetic energy, it's slowly going to lose its kinetic energy until it gets to zero. And these electrons are really going to try and interact with it as it's moving along. Being that I like to use metaphors, I'm going to do that just now. And I have a choo-choo train right here. Don't judge my drawing skills. And this choo-choo train is moving on a track, and it's a big, big, massive train. And it was given a push, you can say, and it's doing 100 kilometers an hour, and its engine shut down, so it's slowly going to decrease. The velocity is going to decrease until it gets to zero, until it stands still. What's interesting is that along the track there are a bunch of people everywhere that really, really want to get on this train. These people are all very impatient, kind of like Israelis. They're all super very impatient. So you can imagine that they really want to get on the train. So what would happen? How would these people, or you can think of it, how would these electrons will be able to interact with this huge, massive, kind of like alpha particle moving object? So remember, these people are really, really attracted to this train. So what would happen? This train is going to start moving really, really fast, right? It's got some kinetic energy to it. It's doing 100 kilometers per hour, which is really fast. So not a lot of people are going to be able to jump the train. Maybe only highly trained special forces Israelis are going to be able to jump the train at this speed. But the slower it gets, let's say we're talking about 40 kilometers an hour. Maybe some very skilled children are going to also be able to jump the train. So I'm going to be having more interaction. More people are going to be able to jump the train. And as it's almost decreasing to zero, 20 kilometers an hour, I bet that if you really tried, maybe you'd be able to jump a 20-kilometer-an-hour train. So more people, even more people are going to be able to interact with it. Even more people all around it are going to be able to interact with it. So what we can say is that the slower the train gets, or the slower the particle gets, the more interactions it would have with its environment. And really the interactions an alpha particle, which is a very highly charged particle, has with its interactions is ionizations. And why? Because if electrons are jumping on the train, if electrons are jumping to get to this particle, they're leaving their atoms. So their atoms are left ionized. So this alpha particle effectively travels through the tissue and ionizes uh, electrons. And what's important to understand, which we pretty much understood from this little idea here, is that the faster I'm going, the less ionization I'm going to cause. So the faster I'm going, the less people are going to be able to jump on the train. So in other words, the transfer of energy is inversely proportional to the kinetic energy of the particle. And what I really mean is that if I have a lot of kinetic energy, I'm moving really fast, I'm not transferring a lot of energy. But the slower this train gets, if the kinetic energy is lower, it's transferring a lot of energy because a lot of people are able to jump on board. And now that we know that, how an alpha particle behaves, we can understand this graph. And on the y-axis, I have how many ion pairs were generated, or rather, how much interaction did I have with my environment. And you can see, and also in the x-axis, we have the penetration depth, or how far did the train go. And you can understand that it goes, the further it goes, the slower it travels. So it's really the same thing. The further I am in my material, the slower I'm going to actually go because I'm not gaining more energy. I had energy to begin with and I'm slowly losing it. So you can actually see that the further I go in the material, I have a certain energy. I'm having 100 kilometers an hour at this point. But when I get to 60 kilometers an hour or 40 kilometers an hour, I'm actually producing more interactions with my environment. I'm producing more ion pairs, or more people are able to jump the train when it's going slower. And when the train is really, really almost stopped, the maximum amount of people are going to be able to interact with it. And then after it stops, there's no more interaction. And why? Why is there no more interaction after it stops? Well, what happens to two protons and two neutrons when it's stopped entirely and two electrons are interacting with it? Let's just say two last electrons interacted with it and they place themselves in the orbitals, and now it's a helium atom. And helium doesn't like to interact with its environment at all. It's a noble gas. It's inert. So once we have two electrons in the orbital, it doesn't really produce any more ion pairs, and it just drops. There's no more ion pairs generated. And the Bragg peak is really the point at which the kinetic energy of the alpha particle is decreased to zero. So that's pretty much it. That's how an alpha particle behaves, like a big fat train that is moving around and a lot of people are going to want to jump it. And the electrons can really jump on this alpha particle only as it's slowing down. So the slower it gets or the further it gets in the material, the more interactions or more ion pairs it's going to generate. So being that we mentioned the beta particle, let's consider what might it do. And we already compared an alpha particle to a beta particle. And a beta particle is, first of all, it doesn't have as much charge as the beta particle. And disregard the negative to positive. It's just the amount of charge. So you can think of it as -1 to +2. So +2 is twice the charge. This is only half the charge. And it's a huge fraction of the mass. So a beta particle is going to be able to penetrate a lot deeper because of these factors. It's going to be able to get a lot deeper into the material than an alpha particle. What would occur? And just as we were accelerating electrons in our X-ray tube, we can actually cause a lot of interactions. We can cause other electrons to bounce off, and those electrons are going to ionize maybe K shells, and they're going to ionize some material, et cetera, and they're going to cause a lot of different ionizations and a lot of interactions. This is basically what happens here. We can just jump to the graph because it's so easy to understand. Just imagine this is the tissue. You can think of it, this is my arm. And the beta radiation particle, the electron essentially, is just moving towards my arm here. And as it's entering my arm, it's going to bounce off of different atoms, ionizing, causing ionizations to different molecules. So if this is my electron and I have, let's just say, a nucleus here, this is a nucleus within my tissues in my arm. It is going to get over here, get some electrons to bounce off. It's going to cause ionization, or maybe it's going to bounce here and give some energy and cause electrons to jump up and get excited. And it's going to just keep on bouncing. So if I have, let's just say I have one atom here, one atom here, one atom here, another here. It's all around. This is just dense tissue. My electron can just go boom, 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 just like a pinball machine. And it's going to essentially interact potentially with a lot of atoms. And this is what we have here. We have the electron just bouncing off just like a pinball machine. And it can either ionize and cause electrons to be shot off of atoms, or it can excite, atoms. Let's just say this is the energy levels that we already learned. If this is electron in the ground state, this is just a happy tissue, and suddenly an electron comes and goes boom, and then this electron goes up and it gets excited, and the molecule gains energy, and it gains and it vibrates maybe and rotates maybe. So this is the impact a beta particle, and again, only a beta negative particle, right? Only an electron is going to have with its environment. It is going to cause ionization, excitation. It's going to bounce off different material, and it's going to have a lot of penetrability because it's so small and it's not that charged. There we go. So this is what a beta negative particle would do. And all we have left to discuss really, and the beta positive, we already discussed that beta positive really undergoes annihilation, and we have 2 gamma photons. This is from the last video. You can review that. And let's see what a gamma photon would do. And this is really what it gets interesting. Not difficult, only interesting. So what would occur? I already know from the presentation about X-ray, and maybe it may be a good time to review that. When I have a nucleus here and I have an atom here, right? And I have electrons, I'm going to switch pink for electrons in its orbitals, and I have a photon coming in. It can interact in one of 2 ways. One of them is going to be the photo effect, where it imparts all of its energy and causes an electron to shoot out. Or it can interact in a Compton effect, where it just transfers some of its energy, loses some energy, keeps on going, and one electron is shot out, and then maybe it interacts with another atom and another electron is shot out. But basically, this photon is going to lose all of its energy, and it's going to leave behind a lot of bouncing electrons, or maybe just one bouncing electron. So let's think of what's going to happen. We already said that this photon coming in is going to ionize electrons. And how do electrons behave in material? Just like we already described. So the gamma radiation, if you will, is going to leave a trail of these events behind it. And just to simplify things, this depiction shows a photo effect where this photon here lost all of its energy, and it shot off an electron, it ionized an electron. And that electron behaved just like the last graph. It behaved just like a beta negative or electron particle would behave. So it's going to bounce off, causing ionization and excitation, etc., etc. And basically, the ionization and excitation is mostly going to be done by the beta particle. Look at the path it's going through. And that is why gamma radiation is called secondary ionizing radiation. And why secondary ionizing radiation? Because in effect, as it's entering the material, it is going to cause ionization of electrons, and those electrons are going to cause the majority of the chaos or in the ionization and excitation events in the material. And this is how gamma radiation interacts. Gets in, turns into an electron or even a bunch of electrons. Think of a few of these branches going in every direction if we're talking about a gamma photon that actually succeeded in ionizing a few of these electrons. So we discussed how an alpha particle behaves, how a beta negative particle behaves, and how gamma photons behave. And these are ionizing particles, and this is a secondary ionizing radiation, the gamma radiation. And all we have left to discuss is how do we characterize these different radiations? Well, we already mentioned penetrability. How much can I penetrate into my material? And if we're talking about penetrability, we can either say high penetrability or low penetrability. And we're not really going to give units. We're going to keep it simple because basically in biophysics entry-level course, we're asked to either compare between an alpha particle to a beta negative particle or an alpha particle to a gamma particle or a gamma photon. So we're going to expect high penetrability from gamma photons and negative beta particles. And we're going to expect low penetration from alpha particles. And why can we expect low penetration? For two reasons. First of all, it is very massive. So it's got 4 atomic mass units. And if you compare it to a photon that has no mass, or you compare it to an electron that is 1 to 2,000 or even less than that atomic mass units, these are small particles that can penetrate deeper, and this is a huge, massive particle. And also its charge is double the charge of the electron. You're talking about double charge, +2. So it's very highly charged, so it's going to be slowing down because more electrons are going to want to interact with it very massively. And it's also very massive. And that's why it has low penetrability. So alpha particle compared to a beta particle, alpha particle has less penetrability, whereas beta negative particle is going to have more. An alpha particle is going to have less penetrability compared to a gamma photon. Perfect. And now it's a good time to mention LET, and by LET we meant linear energy transfer. What's important to understand about that is that we have another way of saying LET, which is the expression ionization density, and that's the exact same thing. And the reason I'm going through both is that you may encounter both, and actually you are encountering both in the lecture slides or some notes or maybe even the exam. They may say ionization density. And ionization density and linear energy transfer are the same. So what you may ask is, what are those? What are those? Well, basically, linear energy transfer is exactly what it is. It is basically asking, how much energy can I transfer to my surrounding? And as you can imagine, the linear energy transfer to its surrounding is proportional to the charge and to the size. So this train is going to be able, this huge, massive, very highly charged train is going to be able to impart much more energy to its environment when it's slowing down. Much more than this particle that is not charged at all. It's only secondary ionizing, and this particle that is only slightly charged and very, very small, and it's not going to impart a lot of energy. It's going to lose its energy in several steps, maybe interact, bounce off of different particles, but compared to the alpha particle is not going to have such high linear energy transfer. Just think about the alpha particle as a very massive train that can impart a lot of energy to its surrounding. So if we compare, let's do green for LET. So if we compare LET, alpha particle compared to a beta particle have way more LET, way more. And also it has way more LET than a gamma photon. And actually alpha particle has the most LET out of all the different radiation emitted particles that we are going to examine. But when you're thinking about it, LET is the highest for an alpha particle, and penetrability is the lowest for alpha particle. This is what we really need to know in respect to penetrability and LET. And again, there are other constituents, but we're only going to be asked to compare this guy to these two guys. You're not going to actually need to make a comparison between these two because it's kind of a tricky comparison. Just remember, the small guys penetrate more, but they impart less energy. Perfect. And all that's left to discuss is the detection of radiation. And this is obviously we have the Geiger-Müller counter, which you will encounter in labs. But what I really want to talk about is the main player in the arena. And this is the scintillation detector and the photomultiplier tube, which really work in succession to give us some idea as of what's going on. And I only have this drawing, and being that there's a lot of names and a lot of arrows drawn in, I'm not really going to use this right now. I'm just going to have this on the side. And I'm going to draw it from scratch. I'm going to draw it from scratch. Very good. So what I really want to use this is I want to take this little guy here, which is commonly referred to as a scintillation detector, although the scintillation part is only this part, and this part is the photomultiplier tube. But basically, this detector tells me, it can give me information about my radiation. How do I do that? Well, it's a good question. I take this part right here, and I face it towards the radiation source. And we already know that radiation, any type of radiation, would be associated with some sort of gamma photons. So this is what I'm going to look at. So basically, this side is facing the radiation, and this side is, let's just say, it has wires attached to it. It's going to a computer, and it's going to measure. It's going to measure current. It's going to measure net charge that flows through it. So essentially, I need a way to turn a gamma photon to current, and this is what we are going to do. Now, what is going to happen? We're going to have a photon coming in and read at the scintillation detector, and is going to be turned into a flash, And this flash is just going to travel through the material of this crystal. You can think of it as a crystal because it is. So it's going to be turned into a flash. And if I'm going to zoom here just for a second, let's zoom here. And I have my photon is coming in, and then the property of this crystal is that it takes this photon and it just turns it into a flash that is traveling across. And what you can think of it as doing is that when it gets to the end, we have this tube. It's called the photomultiplier tube. It's this guy here. When it gets to this tube, these little incident light flashes are going to be turned into electrons. And you already know that there's something going on here. We're almost there. And what's interesting is that a single electron is not really a whole lot of current, and I need to really have something I can measure. So I need to find a way to multiply this charge, or to turn this photons that were turned into electrons, or this incident photon turned into electron, and multiply it in the tube, or a photomultiplier tube. And how does that work? Well, we already know that these electrons, if I put some sort of positive charge here, they're all going to get to it. And to keep things simple, let's just say one electron was liberated, it's going to get to it. Let's just say I have a plus 80 charge here. Now, if it's, let's say, even a plus 800, if it's such an enormous charge, this electron is going to shoot off so quickly, it's going to cause a secondary electron to be emitted from this plate here. So let's just say I have another plate right next to it, and it's charged plus 2000. And when the electron gets here, it goes, oh man, this is super charged, let's get there. And the electron here that had so much kinetic energy, it created a secondary electron. Then we're going to have two electrons that are going to gravitate, or going to move towards this plate. And these electrons were also so powerful when they impacted the plate, they're going to cause the jumping of two additional electrons. And what's happening next? Well, I have another plate here that's charged plus 4,000. And I have these two electrons with the other two guys that were also ejected. And all four are going to gravitate really, really fast towards this next plate. And you can see how this keeps multiplying and keeps multiplying until it gets to the very end, where I have a bunch of electrons that now I can get a firm reading for currents. So I'm going to have these plates, and these plates are called diodes. Diode. And that's because they can function both as a cathode and as an anode, because they successively increase in charge. So they successively increase in charge, and then it gets to the very end. So if I try to make a point to draw this, I have one electron. Let's say only one electron was liberated from this crystal. I have one electron that impacts it with such a strength that it causes an ejection of another electron, and both electrons now move towards the second diode. And then I have 4, and now I have 8, and then I'm going to have 16 and 32 and 64 and 128 and 512 and etc., and 10, 24 and 248. And at this point, what happens is I have a bunch of electrons that now I can really read as current, because first I had one electron. That's not really a reading. That's not enough for our instruments. We need to really find a way to multiply. So if I'm looking at this little drawing here, we have the photon coming in. This is where the particle is coming in. This is the crystal that turns it into a flash, and this is where the electron is liberated. And you can see the successively increasing charge of the diodes, and you can see that when I have 2 electrons hitting here, then 4 are liberated, and so on and so forth. And the only reason that I hang up on making sure that you understand this is that A, it is in the minimals, and B, pretty much quite a few of our imaging methods that we are going to discuss will use these photon multiplier tubes. So hopefully you found this helpful. And this seals the deal for the presentation about radiation. And we're going to move on and take care of the ideas of what happens with radiation and biological tissues. See you soon.